Good evening, and welcome to The Sleepy Scientist. Tonight's journey drifts through the deep calm of space to explore how galaxies are born, how from darkness and dust the universe quietly learned to shine. So settle back, dim the lights, and let your mind wander among the stars. Before we begin, I'd love to know, where in the world are you watching from tonight? It's always fascinating to see our little community scattered across this wide planet, each of us gazing up at the same ancient sky. If you enjoy these calm explorations, a gentle tap on the like button really helps more curious dreamers find their way here. And if you'd like to join us for more quiet stories of science and wonder, consider subscribing. To those already part of the Sleepy Scientist family, thank you for your steady company. And don't forget to ring the little bell so you'll be gently reminded when the next journey drifts in. Now, I can only hope the video isn't too interesting and ends up keeping you awake, but if it does, at least you might fall asleep a little wiser. So how did the universe, once silent and dark, craft its first islands of light? In the beginning, the universe was calm, expanding gently after its fiery birth. No stars, no galaxies, no light, only a soft, cooling fog of hydrogen and helium drifting through endless space. Yet even in that stillness, something subtle stirred. Tiny ripples in the fabric of matter, almost imperceptible differences in density, began to grow under the slow pull of gravity. These small imperfections were the seeds from which everything else would rise. The story of galaxy formation begins with these whispers in the cosmic sea. Over hundreds of millions of years, matter flowed together along invisible threads, weaving the vast structure we now call the cosmic web, a network of filaments stretching across the observable universe. Within its knots, the first galaxies would one day ignite, lighting up the darkness like distant embers. But galaxies are not simply clusters of stars. They are the universe's way of organizing chaos. Inside them, physics becomes poetry, gravity sculpts, radiation paints, and time conducts the quiet orchestra of creation. From the smallest dwarf systems to the grand spirals we see today, every galaxy carries within it a memory of those early ripples, the faint echo of the universe learning to take shape. Tonight we'll wander slowly through that story, from the first faint glimmers of starlight to the majestic spirals that now wheel through space. We'll see how invisible dark matter built the scaffolding for everything luminous, how gas cooled and condensed, how stars were born, and how galaxies collided, merged, and evolved into the graceful forms that fill the night sky. It's a tale written across billions of years, unfolding in silence. And as we drift through it together, you might find yourself wondering, when the universe first opened its eyes, what did that first light look like? In the earliest moments of cosmic history, the universe was a quiet ocean of simplicity. The great fire of creation had already burned, expanding and cooling until its fierce glow dimmed into a soft, pervasive afterlight. The faint microwave hum we can still detect today. It was a time before stars, before galaxies, before any true light had learned to shine. Imagine a vast expanse filled only with an invisible mist of hydrogen and helium evenly spread, almost perfectly smooth. Almost. Because hidden in that calmness were tiny irregularities, ripples so small they might seem meaningless. Some regions held just a whisper more matter than others, a part in 100,000 difference. But these faint variations, these cosmic murmurs, were enough to change everything that followed. For in the slow patience of the universe, gravity has an ear for even the softest sound. As the universe continued to expand, it also cooled. The high-energy particles of its youth slowed and settled, allowing atoms to form, simple hydrogen and helium combining into the first true ingredients of matter. space itself was still glowing faintly, the light from the Big Bang stretching and softening into that now famous cosmic background. It wasn't bright, it was a gentle, uniform radiance, like the faintest ember of a fire that refuses to go out. Yet in that near perfection, gravity began its long, deliberate work. Wherever the density was slightly higher, the gravitational pull was slightly stronger, and that meant it could attract more material. Slowly, invisibly, those small regions grew denser still. The process was painfully slow, far slower than anything we could ever witness directly. But time, after all, was something the universe had in abundance. Picture a vast dough left to rise overnight in a quiet kitchen. Nothing seems to be happening when you glance at it, but come morning it has expanded beautifully, shaped by invisible forces of pressure and patience. The early universe was much the same, subtle changes accumulating over ages, each tiny clump growing a little denser, a little warmer, until the smoothness began to break. The physics behind it is simple yet profound. Gravity, the same force that keeps your feet on the ground, has no preferred scale. It will act across inches or across billions of light years, so long as there's mass to pull. And because the early universe contained everything there was, gravity had the ultimate canvas to work on. Those faint ripples of density were the first brushstrokes on that cosmic canvas, sketching outlines of the structures to come. But gravity isn't the only artist here. As matter gathered, radiation, the leftover light from the Big Bang, pushed back. This created a kind of cosmic tug-of-war. In denser regions, gravity pulled atoms together, while radiation pressure tried to scatter them apart. These oscillations rippled through the young cosmos like sound waves, and even today, astronomers can still read their faint imprint on the cosmic microwave background, a frozen record of the universe's first harmonies. Over the next few 100 million years, the universe entered what's poetically called the cosmic dark ages. There was no light from stars yet, only the dim afterglow of the Big Bang slowly fading into invisibility. It must have been an almost inconceivable quiet, a cosmos at rest, yet secretly preparing for something extraordinary. Within those dark seas, the tiny density ripples continued to grow, forming invisible clouds of matter that deepened their gravitational wells. These would one day become the hidden foundations of galaxies. If you could somehow float there, in that young, silent universe, you'd see almost nothing at all. There would be no stars to guide you, no galaxies glowing in the distance, only the vast, diffuse glow of the background radiation fading as space expanded. But in every direction, imperceptibly, matter was moving, ever so slightly, ever so patiently, toward places where it was just a bit thicker than average. Like dew collecting on cool grass, the gas began to gather in unseen hollows of dark matter. The dark matter, though invisible, played a crucial role. It provided the gravitational scaffolding upon which everything else would form. Without it, the ordinary gas, the hydrogen and helium that would later ignite into stars, wouldn't have had enough gravitational pull to clump together. The dark matter created the valleys, and ordinary matter, obeying gravity's gentle persuasion, drifted in like fog into a hollow. Each of these growing concentrations was tiny by cosmic standards, perhaps only a few thousand light-years across, but they mark the beginning of structure in a universe that had once been nearly featureless. The first small halos of matter condensed, surrounded by darkness so complete that it would remain unbroken for millions upon millions of years. As the universe aged, more of these halos began to form. They didn't appear all at once, but slowly, like scattered seeds taking root across a garden the size of everything. Over time, the larger ones would pull in smaller neighbours, merging and reshaping themselves, building complexity from simplicity. Every clump of matter, no matter how small, was a participant in the slow choreography of creation. To think, all the grand spirals and glowing nebulae that now fill the night sky were once mere whispers in a smooth, invisible fog. Every galaxy, the Milky Way, Andromeda, and billions beyond, traces its lineage back to those early ripples in the density field, those minute imperfections in a once uniform sea. The universe didn't need drama to begin. It needed only time, patience, and the quiet pull of gravity. And in that quiet, something miraculous was set in motion. The first cold clouds of hydrogen and helium began to fall into the deep wells carved by dark matter. As they did, they heated up from compression, then slowly cooled again as radiation escaped, a delicate balance that would eventually allow the first stars to form. But for now, in this calm and unlit universe, the stage was merely being set. If you could listen to the universe then, it wouldn't be silent, not entirely. The fluctuations of matter and light would hum faintly in microwave tones, stretching with the expansion of space, like a long, slow note fading into infinity. The early cosmos wasn't empty, it was full of potential, humming softly with all that was yet to be. And so, before the first spark, the universe was a study in patience, a quiet, cooling expanse, shaped by the smallest of imperfections, a place where gravity worked gently in the dark, sculpting invisible forms that would one day shine as galaxies. The cosmos, it seems, didn't rush to create beauty. It let the dough rise slowly and silently until one day light would finally break the long night. As the universe continued to expand and cool, the small ripples that once marked the difference between nothing and something began to stretch, deepen, and intertwine. Gravity, always patient and always precise, drew matter together where those faint overdensities lay. Regions with just a touch more material than their surroundings became gravitational magnets, slowly pulling in nearby gas and dark matter. Meanwhile, the emptier regions, the underdensities, continued to expand, leaving behind enormous cosmic hollows. This delicate interplay gave rise to one of the most breathtaking structures in nature, the cosmic web. It is not a metaphorical term, but a literal one. The universe really did spin itself into a vast three-dimensional lacework of filaments and knots, threading across billions of light years. Where filaments met, dense nodes formed, the birthplaces of galaxies and clusters of galaxies. Between these filaments stretched enormous voids, regions so empty that they could contain entire galaxies yet remain almost devoid of matter. If the early universe had been a calm sea, it was now learning to ripple in grand style. The first clumps of matter began to connect through these invisible filaments of dark matter, which acted as cosmic highways guiding the flow of gas. You could imagine it like dew gathering along spider silk, collecting at intersections, glistening softly in the dark. Except here, the threads were made of gravity, and the dewdrops were galaxies not yet born. This web wasn't something that appeared overnight. In fact, it took hundreds of millions of years, and then billions more, for it to take shape. The scale is staggering. The largest filaments can stretch over hundreds of millions of light years, vast bridges of matter connecting clusters that themselves contain thousands of galaxies. And yet, in its essence, the cosmic web is a product of simplicity. It's the same basic rule applied again and again. Gravity attracts, expansion stretches, and time smooths the rough edges. From our modern perspective, astronomers have mapped this web using galaxy surveys and simulations, revealing patterns that look remarkably like living tissue or the neural structure of a brain. It's tempting to imagine the universe as a cosmic organism, its filaments pulsing faintly with the light of billions of stars, It's voids, the dark spaces between cosmic thoughts. But of course, it's not alive. It's simply the outcome of physics unfolding with elegance and patience. Still, it's hard not to admire the artistry. If the universe had a hobby, weaving would be its finest craft. The cosmic web is not the product of haste. It's the result of billions of years of slow, continuous weaving, an interlacing of gravity's threads across space-time. The universe is in many ways a world-class slow weaver. The process of this weaving can be described not through complicated mathematics here, but through rhythm and balance. Where matter gathered, gravity strengthened, pulling in even more. But where matter was scarce, expansion pushed outward more efficiently, leaving behind vast bubbles of emptiness. Over immense spans of time, this balance carved the large-scale texture of the cosmos, clusters, filaments, and voids, repeating across the universe in fractal-like beauty. If you could step far enough back, impossibly far, and look at the universe from outside, you would see something astonishing. Not a uniform fog, but a great sponge-like pattern, dense in places, hollow in others. Galaxies would trace delicate strands, glowing faintly like lights along unseen bridges. Between them, immense voids would stretch in every direction, dark and silent. This is the architecture of everything we see in the night sky, built not by chaos, but by harmony. Dark matter is the silent architect of this cosmic lacework. Although we cannot see it directly, we know its presence by the way it bends light and guides galaxies. Its gravity shaped the scaffolding long before ordinary matter, the gas and dust that make up stars and planets, had cooled enough to join in. As gas followed those dark threads, it began to collect in knots, heating up and preparing to form the first stars. But at this stage the web was still mostly invisible, waiting to glow. The beauty of this process lies in its slowness. Galaxies, clusters, and filaments didn't appear all at once. They emerged over time, as if the universe was sketching lightly before committing to bold strokes. If you could somehow accelerate time, play the cosmos like a time-lapse film, you would see streams of matter flowing along invisible ridges, coalescing at junctions, brightening as they gave birth to stars. The web would shimmer, faint at first, then blaze with new light. And yet, even in this grandeur, the underlying principle remains humble. It's the same physics that governs a droplet forming on a window pane or dust collecting under furniture. Small differences amplifying over time. The universe is simply the largest version of that rule imaginable. Tiny inequalities in density, multiplied over billions of years, become the vast tapestry of cosmic structure. Within this growing network, galaxies would find their homes. Each node in the web, each intersection of filaments, became a cradle for thousands of galaxies, all orbiting and evolving within their gravitational neighborhoods. The voids, meanwhile, grew ever emptier, pushing the galaxies toward the filaments like leaves drifting along invisible currents. This constant motion, the slow breathing of cosmic structure, continues even now. Our own galaxy, the Milky Way, resides on one of these filaments, gently connected to others by thin bridges of matter. If you could trace the Milky Way's position, you'd find it sits within a larger structure called the Laniakea supercluster, a grand flow of galaxies drawn together by gravity, all threading their way along the filaments of the cosmic web. Even our quiet corner of space belongs to this ancient design. The remarkable part is that this design was written into the fabric of the universe from the very beginning. The pattern of filaments and voids, though vast, was encoded in those first tiny ripples in the early cosmos. The universe's large-scale structure is, in a sense, the magnified fingerprint of its birth, a record of the smallest fluctuations grown to monumental proportions. When astronomers look at galaxy maps today, they can trace these filaments like veins of light through the darkness. Each point of light is a galaxy containing billions of stars, yet when viewed together, they reveal the web's delicate geometry. It's humbling, almost poetic, that the universe's grandest form mirrors the quiet patterns found in nature. The branching of trees, the cracks in drying clay, or the filigree of frost on a window. If one lesson can be drawn from this cosmic weaving, it's that complexity often arises from the simplest of beginnings. From the tiniest variations, order emerged. From smoothness came structure. From the whisper of gravity came a grand design spanning the universe. And though it took billions of years to form, the cosmic web is still changing even now. Filaments stretch, clusters merge, and the universe's expansion continues to pull the threads wider apart. It's a creation still in motion, a fabric that breathes slowly, rhythmically, in tune with the heartbeat of time itself. So when you look up at the night sky, every speck of starlight is part of that intricate lace. The constellations you trace are only a small patch in an immense pattern, one that connects everything that ever was and ever will be. The web of the cosmos stretches silently, a masterpiece woven by gravity, one patient thread at a time. Before a galaxy can shine, it needs a place to take shape, a quiet refuge where gas can gather and stars can one day ignite. But this home, this invisible foundation of every galaxy, is not made of the stuff we know. It's built from something that cannot be seen or touched: dark matter. Dark matter makes up most of the universe's mass, yet it gives off no light. It neither absorbs nor emits radiation, which makes it as transparent as empty space. Still, it's there, detectable through its gravity, silently shaping the cosmos. Astronomers call the great clouds of this unseen substance halos. Every galaxy you can see, from tiny dwarfs to immense spirals, lives within one of these halos, like a firefly drifting inside a vast invisible bubble. Imagine the universe as a landscape made of gravity rather than soil. Dark matter creates the hills and valleys in that terrain. Wherever it pulls densely, the gravitational pull deepens, forming what physicists call a potential well. Into these wells, ordinary matter, hydrogen, helium, dust, slowly falls, much like morning mist collecting in the low valleys of a still landscape. Without the pull of dark matter, that mist would simply drift away, never condensing enough to form the stars and planets that give a galaxy its glow. The story of how dark matter halos form begins in those same tiny ripples that once filled the young universe. Where the density was slightly higher, dark matter particles clumped together under gravity's steady hand. These small clumps, or proto-halos, began to grow as they attracted more and more dark matter from their surroundings. Over time, the small halos merged into larger ones, and those into larger still, a process astronomers call hierarchical growth. It's a bit like cosmic nesting dolls, each one swallowing the smaller, older ones inside. Most halos, however, remain small. For every massive halo that will someday cradle a grand spiral galaxy, there are countless little ones, faint, quiet pockets of gravity scattered through space. The universe is full of these invisible structures, forming a hidden architecture beneath the luminous web of galaxies. The larger halos may span hundreds of thousands of light years and hold masses equivalent to trillions of suns, while the smallest ones might be no bigger than a globular cluster, holding the faintest glimmer of potential starlight. The reason these halos are invisible is simple. Dark matter doesn't interact with light. It passes through ordinary matter, through stars, even through us, without so much as a flicker. Yet its gravity shapes everything. It is the silent scaffolding of creation, unseen, unyielding, and absolutely essential. The universe's grandest structures owe their form to this ghostly material that never shines. If dark matter is the scaffolding, then gas is the plaster that fills it in. As hydrogen and helium drift into a dark matter halo, they heat up from compression, glowing faintly in ultraviolet and X-rays before cooling again. Over millions of years, this gas settles toward the center, becoming dense enough for the first stars to ignite. Without the halo's gravitational cradle, that gas would never stay together long enough to form anything at all. The physics of halos can be imagined through the simplest of analogies. Picture a countryside at dawn, where cold air has pooled in gentle valleys overnight. As morning arrives, mist gathers at the lowest points, collecting softly where the land curves inward. The surrounding hills remain clear, while the valleys fill with delicate fog. That's precisely what dark matter halos do. They are the valleys of the cosmic landscape, collecting the gaseous mist of ordinary matter and allowing galaxies to take shape within. Even now, billions of years later, these halos continue to guide the dance of galaxies. Each halo forms a gravitational boundary, defining the region where a galaxy's stars, gas and dark matter all remain bound together. Outside that region, space belongs to another halo, another system, another cosmic valley. These boundaries aren't sharp but gradual, blending into the greater fabric of the cosmic web. Astronomers have become remarkably good at inferring the presence of these halos, despite never seeing them directly. One method involves the motion of stars and gas within galaxies. In the 1970s, astronomer Vera Rubin made a revolutionary discovery while studying how galaxies rotate. She found that stars at the outer edges of galaxies were moving far faster than expected, as if an unseen mass was tugging on them from every direction. That unseen mass, much greater than all the visible stars combined, was the dark matter halo. Today we can even map the shapes of halos using a technique called gravitational lensing. When light from distant galaxies passes near a massive halo, gravity bends the light, distorting it slightly. By measuring those distortions, astronomers can trace the invisible contours of the dark matter itself, revealing the hidden bones of the universe. Halos don't just host galaxies, they also govern how galaxies evolve. The mass of a halo determines much about the galaxy it shelters. Small halos tend to form small, fragile galaxies, faint dwarfs easily disrupted by supernova winds or nearby giants. Larger halos can hold onto more gas and grow vast, stable systems like the Milky Way. And in the most massive halos, the pressure and heat become so intense that new star formation slows, leaving behind immense glowing ellipticals surrounded by clouds of hot gas. This hierarchy, many small halos, fewer large ones, gives the universe its rich variety. It's the reason we see countless small galaxies alongside a handful of truly giant ones. It's why galaxy clusters contain a mix of shapes, sizes, and brightnesses, all bound together in one vast gravitational family. Each halo is like a village in the grand geography of the cosmos, with its own history, its own rhythm, its own quiet balance of forces. The nature of dark matter remains one of the universe's most enticing mysteries. We know it's not made of ordinary atoms, it doesn't emit or absorb light, and it doesn't collide with itself the way normal matter does. It could be made of exotic particles that rarely interact with anything, candidates like WIMPs or axions, names that sound almost whimsical for such serious cosmic suspects. Despite decades of searching, we still don't know exactly what dark matter is, and yet we can trace its fingerprints everywhere, in the way galaxies move, in the patterns of the cosmic web, in the very shape of the universe itself. Perhaps the most poetic thing about dark matter halos is how their presence gives rise to beauty without ever revealing themselves. They are like the unseen strings beneath a musical instrument, vibrating quietly to hold the melody together. Without them, the universe would still be a cold fog of scattered atoms. No stars, no planets, no life to observe it all. So when we look at the night sky, every gleaming spiral and glowing cluster is only the visible half of the story. Beneath each one lies a vast, unseen sphere of gravity, a silent structure that makes the luminous possible. Galaxies drift in these halos as mist rests in morning valleys, suspended by invisible hands. In the end, dark matter halos remind us that not all foundations must be visible to be real. The universe's greatest builder works unseen, shaping worlds through quiet persistence. And though its form may forever remain hidden, its influence shines in every starlit sky. A gentle whisper of the invisible sculptor that gave galaxies their home. As the dark matter halos deepened their invisible wells, they began to draw in the universe's ordinary matter, the thin gas of hydrogen and helium that had drifted through the cosmos since its earliest moments. Slowly, gently, this gas started to fall inward, pulled by gravity into the waiting hollows. What began as a faint haze across the universe was now being gathered into concentrated clouds, and though the process was unimaginably slow, the first steps toward illumination had begun. When gas falls into a dark matter halo, it doesn't simply settle quietly. Like a stone falling through air, it gains energy as it descends, converting gravitational potential into heat. As a result, the infalling gas can become incredibly hot, millions of degrees in the most massive halos. This superheated plasma emits a faint glow of X-rays, invisible to the naked eye but detectable to astronomers with the right instruments. It is the universe's equivalent of friction, energy turned to warmth as matter meets gravity. But the story doesn't end there. If the gas remained hot, it would never condense enough to form stars. To truly build galaxies, it needed to cool again, to shed its heat through the quiet process of radiation. Atoms and electrons bump into one another, emitting light as they do. Bit by bit, the gas releases energy, its temperature dropping slowly as it radiates away that excess heat into the growing darkness. The universe, in a sense, exhales, a long cosmic sigh that cools the material from which galaxies will bloom. Once cooled enough, gravity's grip tightens further. The gas can now sink deeper into the halo, compressing under its own weight. As it does, angular momentum, the tendency of spinning systems to preserve their rotation, begins to shape the falling gas into a disk. Even the smallest initial spin, perhaps imparted by the early tug of neighbouring halos, grows stronger as the gas contracts. The tighter it gathers, the faster it spins, much like an ice skater drawing in their arms. Over time, these rotating disks become the cradles of new galaxies. Streams of gas circle the centre, colliding gently and settling into ordered motion. Within these spinning structures, turbulence and density, fluctuations create the perfect environment for the next great step, the birth of stars. Star formation begins not with brilliance but with thresholds, conditions of temperature, pressure, and density that determine when gravity can overcome internal resistance. Gas that's too hot resists collapse, while gas that's too diffuse drifts apart. But when the balance tips just right, gravity wins. In the densest pockets of the cooling gas, regions begin to collapse inward under their own weight. Molecules form, temperatures fall, and the fragments shrink until their centres grow hot and dense enough to ignite nuclear fusion. It's a process that requires astonishing patience. The timescales stretch across tens or even hundreds of millions of years, each step slow and deliberate. The universe is never in a hurry, it builds with care. And somewhere within those dark halos, as gas cooled and swirled, the first sparks of starlight flickered into being. The physics of this transition from gas to light is deceptively simple, yet profoundly beautiful. Hydrogen, the simplest and most abundant element, becomes the fuel for everything that follows. When two hydrogen nuclei fuse, they form helium and release energy, pure radiant light. That light, escaping the heart of the newborn star, announces the universe's next era, darkness giving way to illumination. But even before the first stars fully ignite, the cooling gas itself contributes to a faint ghostly glow. As atoms transition between energy states, they emit subtle lines of radiation, a kind of soft fluorescence that marks the process of cooling. This glow, invisible to our eyes but traceable with modern telescopes, was the first hint of the cosmos stirring from its long, cold slumber. As more gas fell in, the disk thickened and flattened, its rotation steadying the turbulence. Within it, regions of higher density began to fragment into smaller clumps, each collapsing into its own cluster of stars. These early star clusters illuminated the surrounding gas, heating and shaping it, creating bubbles of light within the larger halo. Slowly, a balance emerged. Cooling gas feeding the birth of stars, and starlight heating the gas in return, keeping the system in gentle equilibrium. The shape of these early galaxies depended greatly on the size and spin of their halos. In small halos, cooling was quick and efficient, leading to compact, intense bursts of star formation, galaxies that burned bright and brief. In larger halos, cooling took longer, allowing vast disks to form, where star birth proceeded steadily and gracefully over billions of years. Each galaxy carried within it a record of this early dance between heat and gravity, a unique fingerprint of its origins. The beauty of it all lies in the interplay between the violent and the serene. On the one hand, gravity is relentless, collapsing, compressing, heating. On the other, cooling is gentle, the slow release of energy, the quiet radiance that allows structure to settle and persist. Together, they create a kind of cosmic breathing. Gas falls in and heats, cools and collapses, shines and stabilizes. Out of this rhythm, the first luminous forms are born. If you could watch the process unfold from afar, perhaps over the course of 1 billion years, you would see halos glowing faintly as streams of gas spiral inward, brightening momentarily as they collide and heat, then dimming as they cool again. Eventually, tiny pinpricks of light would appear within them, the first stars flickering like candles in a vast dark cathedral. These were the universe's first beacons, breaking the endless night. From these beginnings, galaxies would continue to grow, drawing in more gas, forming more stars, and shaping their light into the grand spirals and ellipticals we see today. But every one of those galaxies, no matter how vast or bright, began with this same quiet act. Gas cooling in the dark, falling into invisible hands, and learning to shine. There is something almost poetic about the fact that the universe had to cool in order to create warmth. The hottest plasma, blazing with energy, could not produce light in the way we know it. Only when it released that energy, when it slowed, condensed and calmed, did it begin to glow in a way that could fill the cosmos with beauty. Creation, it seems, began not with fire, but with the letting go of it. And so, through the quiet balance of heating and cooling, of motion and stillness, the dark matter halos became the first cradles of starlight. The cosmos, once silent and invisible, now shimmered faintly with the light of its newborn stars, the first gentle illumination of a universe learning how to shine. The moment the first stars were born, the universe changed forever. For hundreds of millions of years, space had been dark, filled only with the faint glow of the cosmic background, fading as it stretched across expanding space. But when the first true stars ignited, their light pierced that darkness for the very first time. The cosmos, after a long and silent childhood, finally opened its eyes. These first stars were unlike any that followed. Astronomers call them Population 3 stars, a simple, slightly poetic name for a generation of suns that no longer exists. They were forged from the purest material imaginable, hydrogen and helium, with no heavier elements at all. The universe at that time was chemically simple, untouched by the complex alchemy of later ages. Without metals, the astronomers' term for anything heavier than helium, these early stars behaved in ways that are difficult for us to fully picture today. Because metals help gas cool and fragment, their absence meant that the first stars were born differently. The clouds that collapsed within those young halos were hotter and denser, and as a result, the stars they formed were giants, true titans of light. Some may have reached masses hundreds of times that of our Sun, blazing far hotter and brighter than anything we see today. They lived fast, burned furiously, and died young. Their light was pure and intense, flooding their surroundings with ultraviolet radiation. For the first time, the darkness was pushed back. The cold hydrogen around them ionized into glowing plasma. Whole regions of space began to shimmer as these early suns illuminated their cosmic neighborhoods. It was the dawn of the universe's first day, and though those stars would not live long, their presence transformed everything. Inside their cores, fusion ran at a ferocious pace. Without metals to regulate energy flow, these colossal stars churned their fuel with chaotic vigor. In mere millions of years, the blink of an eye compared to the long lives of modern stars, they exhausted their hydrogen and helium, fusing them into heavier elements like carbon, oxygen, and iron. For the first time, the universe began to manufacture complexity. The light of the first stars was more than illumination. It was the beginning of cosmic chemistry. And then, almost as quickly as they had appeared, they died. But they did not fade gently. Many ended their lives in violent supernovae, colossal explosions that tore them apart and scattered the new elements they had forged into the space around them. Some may have collapsed directly into black holes, seeds that would one day grow into the supermassive giants found at the centres of galaxies. Others detonated with such energy that their brilliance would have outshone entire galaxies for a brief moment, leaving behind expanding clouds of heavy elements, the universe's first gift of dust and metal. These explosions were, in every sense, creative acts. The heavy elements they released, the carbon that would someday form the backbone of life, the oxygen that would fill lungs, the iron that would course through blood, all began here. Before these first stars lived and died, there was none of it. The universe was clean but sterile, beautiful but barren. The death of these stars made it rich. Their light also changed the behavior of the gas around them. Ultraviolet radiation stripped electrons from hydrogen atoms, creating vast bubbles of ionized gas that expanded outward and merged with others. The darkness between halos began to thin, the great fog of the early cosmos slowly lifting. This process, called reionization, would take hundreds of millions of years to complete, but it began with the light of these first suns. The night was ending and the universe was learning to breathe light. It's humbling to think how ephemeral these stars were. Many likely live no longer than a few million years, a fleeting instant compared to the billions our sun will endure. Yet their brief existence left fingerprints across eternity. Their supernova seeded their surroundings with metals that would later help gas cool more efficiently, giving rise to smaller, longer-lived stars, the kind that could host planets and, eventually, life. In that sense, every person, every world, every atom heavier than helium owes its existence to the death of these first suns. If you could somehow stand in the universe during that era, a thought experiment both impossible and strangely moving, you would see the cosmos as it first came alive. Against a backdrop of darkness, scattered halos glowed faintly, each one nurturing a few brilliant stars. They would not have formed in grand spirals or clusters, but in scattered pockets, flickering on and off across the cosmic web like embers in the wind. Each burst of light was both a beginning and an ending, creation through destruction, illumination through exhaustion. In a way, the first stars were both artists and architects. They painted the universe with light and sculpted it with their explosions. Their radiation carved cavities into the gas around them, their deaths enriched the cosmic medium, and their remnants, black holes and neutron stars, added new complexity to the cosmic story. What followed, all the galaxies and solar systems to come, would rise upon the ashes of their brief brilliance. Astronomers today can't observe these stars directly. They burned out more than 13 billion years ago. But their influence is everywhere. The chemical composition of ancient stars in our own galaxy still bears traces of the elements forged in those first furnaces, and with powerful observatories like the James Webb Space Telescope, we can peer deep into time, to the era just after those first lights flickered into existence. What we see are galaxies in their infancy, faint and red-shifted, carrying the echoes of that ancient dawn. There's something poetic in how the story unfolds. The universe began in light so bright it was blinding, then cooled into darkness, only to find light again, this time self-made. When those first stars ignited, they turned energy into beauty, matter into memory. They were short-lived, yes, but their light still travels across the cosmos, stretched thin by expansion, whispering the story of their birth and death to any who care to listen. The first stars remind us that beginnings are often quiet, and that brilliance can come from simplicity. Out of pure hydrogen and helium, the universe created not just illumination, but the very ingredients of all future complexity. Their brief lives may have ended in silence long ago, yet their legacy endures in every atom of every living thing, in every star twinkling tonight. And as the universe's first dawn spread across the darkness, the cosmos took its first real breath, one filled with starlight, warmth, and the faint promise that, from this glowing dust, something extraordinary was about to begin. The first stars had set the universe aglow, but their light did more than just illuminate the darkness. It began to transform the very nature of space itself. For hundreds of millions of years after the Big Bang, the universe had been filled with a soft, cool fog of neutral hydrogen, a cosmic mist so pervasive that it scattered and absorbed light, obscuring distant horizons. But as the first stars and galaxies ignited, their radiation began to clear that fog away. This was the era of reionization, a time when the universe woke from its long dark slumber and the cosmic morning truly began. It's easy to imagine the universe at this point as a night sky slowly brightening before dawn. In the beginning there were only a few isolated stars, each surrounded by a small bubble of ionized gas, regions where the energy of starlight had stripped electrons from hydrogen atoms, turning the once neutral gas into plasma. These bubbles were scattered and small, like faint lanterns flickering across an endless plain of mist. But as more stars formed and galaxies began to cluster, the bubbles grew larger, brighter, and more numerous. Over time, these pockets of ionized gas began to overlap, merging into great irregular patches of light. The process wasn't uniform, it was messy, uneven, and gradual. Some regions cleared early, others lagged behind, still shrouded in haze. If you could have watched it from above, as though peering down through eons of time, you'd see a universe dappled with light and shadow, a living mosaic of glowing pockets spreading outward until the last remnants of fog finally faded. This transformation fundamentally changed how the universe looked and behaved. Before reionization, the cosmos was opaque to high-energy light. Photons from stars couldn't travel far before being absorbed by the dense neutral hydrogen filling space. But as the fog lifted, the universe became transparent. Light could now move freely across vast distances, revealing the young galaxies and the growing structure of the cosmic web. It was, in every sense, the clearing of the cosmic skies. To the universe itself, if such a vast thing could have feelings, this would have felt like a deep breath after a long sleep. For hundreds of millions of years it had been drifting in twilight, its own radiation trapped within a blanket of gas. Then, with the rise of the first luminous generations, warmth and clarity spread through the void. Space itself became charged and alive again, glowing faintly with the energy of renewal. If the cosmos could sip coffee, this was the moment it finally woke up, the caffeine of starlight kicking in after a very long night. At the heart of this awakening were the young galaxies, small, irregular systems teeming with new stars. Their light was fierce, especially in the ultraviolet, and it was this radiation that did the hard work of ionizing the gas around them. Supernovae added bursts of energy, carving cavities in the surrounding medium, helping the light escape into the wider universe. In some places, quasars, the intensely bright centers of galaxies powered by growing black holes, joined in, acting as cosmic blowtorches that punched through the remaining fog. The scale of this process was staggering. Each ionized bubble could grow to be millions of light-years across, expanding slowly until it met its neighbors. When two bubbles touched, their boundaries dissolved, forming larger regions of clarity. Gradually, the entire universe shifted from being mostly neutral to mostly ionized, a transformation that completed the great transition from the cosmic dark ages to the luminous universe we see today. But it wasn't instant. The era of reionization stretched over hundreds of millions of years, somewhere between about 400 million and 1 billion years after the Big Bang. It unfolded unevenly across space, like sunlight creeping through a landscape of valleys and peaks. Some areas were quick to brighten, home to clusters of vigorous star formation, while others remained dim, isolated, and slow to change. The cosmic web, with its filaments and voids, dictated the tempo of this illumination, ensuring that light spread along the densest regions first, the same filaments that would one day cradle galaxies like the Milky Way. To visualize it, imagine fog on a cool morning beginning to lift. The first rays of sunlight pierce through, creating scattered windows of brightness. As the fog thins, more light filters in, until suddenly the entire scene is bathed in warmth. The era of reionization was the universe's version of that moment. The darkness wasn't defeated by a single grand flash, but by the steady collective light of countless suns working together across the vastness of space. For astronomers today, this period marks a frontier of cosmic history that is only just coming into view. With instruments like the James Webb Space Telescope, we can peer back over 13 billion years to witness galaxies that existed during or just after this great clearing. They appear small, faint, and red-shifted, the light from their young stars stretched by the expansion of space. But they carry the unmistakable fingerprints of the dawn that reionization brought. The physics of it all is simple but profound. When ultraviolet photons from young stars strike neutral hydrogen atoms, they knock loose the electrons, creating ionized plasma. Once enough of these photons flood the universe, the fog of neutral hydrogen can no longer reform. From that moment onward, space remains clear and transparent. The universe has, in a sense, flipped a switch, one that has stayed on ever since. This new clarity had enormous consequences. It allowed light to travel freely, revealing the distant structures of the cosmos. It changed the temperature and chemistry of intergalactic space, influencing how future generations of galaxies would form. And it gave the universe a permanent transparency that allows us, billions of years later, to look back and see those first glimmers of creation. If there's a certain poetic symmetry here, it's that the very act of illumination also brought understanding. The same process that cleared the cosmic fog made the universe visible, not just to itself, but eventually to us. Every observation we make, every telescope that peers across time, relies on the clarity first forged in this era. Without it, the cosmos would still be wrapped in haze, its light forever trapped. The era of reionization marks a turning point, the true beginning of the universe as a luminous, structured place. It is when galaxies began to take on lasting form, when the cosmic web lit up like a network of fireflies, and when light itself became the storyteller of time. From that point forward, the universe was no longer a dark, uniform expanse. It had contrast, texture, and depth. Bright clusters and dark voids, glowing filaments, and star-filled arcs of motion. And so, as dawn spread through the cosmos, the fog lifted and the stars claimed the sky. The universe, once cloaked in darkness, had finally found its light. Every sunrise since, on every planet, around every star, has been a small echo of that first great illumination, when the cosmos woke, stretched its vast arms, and began to see itself clearly for the first time. Once the fog of the early universe lifted and galaxies began to shine freely, the great cosmic architects got to work, not with haste or sudden burst of activity, but with the unhurried patience that defines all of space. Gravity, rotation, and time teamed up to shape the glowing clouds of gas and stars into the elegant forms that now sweep across the heavens. Grand spirals, stately ellipticals, and countless other shapes that trace the quiet geometry of motion. Among these forms, the disk galaxy, thin, rotating, and delicately balanced, became one of nature's favourite designs. The Milky Way is one such creation, a wide, luminous whirlpool of hundreds of billions of stars all moving together in a slow and graceful spin. The secret to its stability lies in a single, universal principle: rotation. When gas falls into a dark matter halo, it rarely does so in a straight line. Every parcel of matter carries a touch of spin, a faint twist inherited from the random motions of the early universe. As this gas collapses inward, that angular momentum becomes more pronounced. Just as an ice skater spins faster when drawing in their arms, the collapsing gas speeds up as it gathers toward the centre. The result is a flattened disk, where the balance between gravity pulling inward and rotation pushing outward creates a quiet, enduring harmony. This rotational support is what gives a galaxy its thin, graceful shape. The stars and gas don't all move randomly, as they would in a chaotic swarm, but follow ordered paths around the centre. Their combined motion smooths out turbulence, transforming what could have been a shapeless clump into a vast spinning plane. Gravity provides the pull, rotation provides the poise, and together they build something remarkably stable, at least on cosmic timescales. If you could view a disk galaxy from the side, you'd see how incredibly thin it is compared to its diameter. The Milky Way, for example, is about 100,000 light-years across, but only a few thousand light-years thick, a cosmic pancake of stars spinning serenely through space. Within that slender shape, billions of suns trace their orbits in near-perfect rhythm, moving fast enough to complete a full revolution roughly every 200 million years. At the centre of many disks lies a bulge, a dense rounded cluster of older stars. The bulge is like the heart of the galaxy, compact and bright, formed early from the violent merging of smaller systems or from the inward migration of stars over time. While the disk rotates in calm unison, the bulge is a place of complex, sometimes chaotic motion, where stars move in all directions rather than a single plane. It adds mass and stability to the galaxy's core, helping to anchor the whole structure. In some galaxies, a bar stretches across the bulge, a bright linear feature made of densely packed stars. These bars act as cosmic conveyor belts, channeling gas toward the center, where new stars are born and where supermassive black holes quietly feed. They're not permanent fixtures, more like slow-moving waves in the galactic sea, forming and fading over billions of years. Yet they add character to galaxies, shaping their evolution in subtle but profound ways. Beyond the bulge and bar lies the main disk, a region alive with motion and light. Here, spiral arms wind outward, not as solid structures, but as waves of density moving through the sea of stars. As these waves pass, they compress gas and trigger bursts of star formation, leaving behind glowing trails of young, hot stars and bright nebulae. It's a pattern of creation and renewal, a galactic heartbeat repeating endlessly across the ages. Spiral arms aren't permanent either. They're patterns, like ripples on a pond, that appear to move through the disk even as individual stars drift in and out of them. The beauty of a spiral galaxy lies in this illusion of permanence born from perpetual change. Each turn of the arms marks the patient work of gravity and motion, combining to sustain order in an ever-shifting world. Some galaxies also form rings, elegant circles where gas and stars gather in resonant harmony. These rings can arise from gravitational interactions or from the steady rhythm of rotation itself, creating zones where star formation flares up in bursts of brilliance. The result is a galaxy that looks almost architectural, as though the universe, in its quiet way, decided to build with symmetry. The stability of these disks, though impressive, is never absolute. They breathe and flex with time. Small disturbances ripple through them. The passage of a satellite galaxy, a collision with a wandering clump of dark matter, or the gentle tug of neighbouring systems. Yet rather than collapsing into chaos, they absorb these disturbances and settle back into balance. Their rotation acts as a kind of self-correcting mechanism, restoring the order of motion that defines them. If you could somehow float above a spiral galaxy, you'd see this balance in motion, glowing lanes of gas swirling toward the centre, dust lanes tracing delicate curves, and star clusters orbiting in vast, slow circles. It would look calm, almost serene, but beneath that calm lies a complex ballet of forces. Every star is moving at hundreds of kilometers per second, yet the combined motion creates a symmetry so smooth that it feels almost still. The galaxy, though vast and dynamic, gives the illusion of rest. What makes this stability possible is the way gravity, rotation, and density balance each other. If the galaxy spun too fast, its material would fling outward into space. If it spun too slowly, gravity would pull it all into the centre. But the universe has a knack for finding the middle ground, a quiet equilibrium where the two forces meet and hold. The result is a cosmic dance that can last for billions of years. Even within this ordered motion, there's room for variety. Some galaxies, like elegant spirals, maintain their disks for eons, while others become puffier and more disordered, turning into ellipticals through collisions or internal evolution. But for those that keep their shape, the reward is longevity. The disk becomes a cradle of ongoing creation, where gas continues to flow, stars continue to form, and the galaxy continues to shine with steady grace. In the Milky Way, the same principles apply. Our sun orbits calmly within one of the spiral arms, taking about 250 million years to complete a single trip around the galaxy's centre. Above and below us, countless other stars follow similar paths, all part of a vast rotating system that has persisted for more than 10 billion years. It's easy to forget as we look up at the night sky that every pinpoint of light is part of this grand machinery, spinning endlessly through space. What emerges from all this slow, circular motion is a quiet kind of order, the kind that only time can sculpt. Gravity may have started the process, but rotation refined it, turning chaotic clouds into the elegant disks that now dominate the visible universe. Each galaxy is a testament to patience, a reminder that beauty often arises not from sudden action, but from steady, enduring rhythm. If the early universe was the universe learning how to light a candle, then disk galaxies are the universe learning how to balance the flame. They represent harmony on the grandest scale, a calm born from motion, stability born from change, and as they turn, endlessly and silently, they remind us that even in a universe built on chaos, there is always room for grace. In the grand stillness of the universe, even collisions happen gracefully. Though the word collision conjures images of chaos and violence, in the cosmos it means something very different. An immense, slow-motion waltz that can last for billions of years. When galaxies meet, they don't smash together like billiard balls. Instead, they drift into one another like two dancers crossing a vast floor, their arms, made of gravity, reaching out long before their bodies ever touch. Galaxies meet because gravity never stops reaching. Over time, the pull between neighbouring systems gently tugs their paths together. The universe itself is expanding, but on local scales, where gravity dominates. Galaxies can still find one another. Clusters and groups of galaxies are like cities in the cosmic web, where encounters are inevitable. Within these gravitational neighbourhoods, some galaxies orbit each other for eons before finally merging, their mutual attraction choreographing a delicate, spiralling dance. The first moment of contact isn't a crash but a whisper. As one galaxy approaches another, tidal forces begin to stretch and distort their shapes. Stars too far apart to collide directly move under the shifting gravitational field, tracing elegant arcs and loops. Streams of gas are pulled outward, forming long, luminous tails that can stretch across hundreds of thousands of light years. From a distance, these bridges of starlight look almost painterly, as if the universe were gently smudging its own artwork. The slow encounter between two galaxies can take hundreds of millions of years, and during that time their structures evolve dramatically. Spirals may twist and warp, disks may tilt or thicken, and bright knots of new stars flare to life as gas clouds collide and compress. These bursts of creation, called starbursts, can outshine the rest of the galaxy for a time, releasing enormous energy as thousands of stars ignite almost simultaneously. Paradoxically, what looks like a moment of cosmic chaos is also a time of creation. At the heart of this process lies the principle of hierarchical growth. The universe builds large structures from smaller ones step by patient step. The first galaxies were tiny, fragile collections of stars and gas nestled within small dark matter halos. Over billions of years these small systems merged, forming larger and larger galaxies. The majestic spirals and ellipticals we see today are, in essence, mosaics, assembled from countless earlier fragments. The night sky is full of survivors of these ancient unions, some peaceful, some tumultuous, all profoundly creative. As galaxies merge, their individual stars almost never collide directly. The distances between them are so vast that even during a merger, stars pass effortlessly by one another, barely noticing. What does collide is the gas, the interstellar medium of dust, molecules and plasma. When these clouds crash together, they compress and cool, creating pockets dense enough for new stars to form. The result is a short-lived but spectacular episode of starbirth, lighting up the merging system like a festival of cosmic lanterns. Eventually, as the two galaxies spiral inward toward each other, their cores draw closer. The dance tightens, stars settle into new orbits, and the remnants of their disks begin to merge into a single, more massive structure. Sometimes the final result is a smooth elliptical galaxy, a grand, rounded system where the old spiral patterns have been erased by the slow blending of stars. Other times, the new galaxy retains traces of its origins, with shells, loops, or faint arcs of light revealing its past encounters. The universe leaves its fingerprints in these faint, ghostly features, reminders of graceful dances long finished. Even our own galaxy, the Milky Way, carries the memory of many such mergers. Its thick disk, its stellar halo, and even some of its star clusters are the relics of smaller galaxies it absorbed over billions of years. The Milky Way is not a single, isolated creation, but a symphony composed from many earlier melodies. And its story isn't finished. In roughly 4 billion years, it will merge with the Andromeda Galaxy, another great spiral on a gentle collision course. Despite the staggering scale, this future meeting will be a slow, silent ballet. The two galaxies will draw closer, their disks stretching and warping as they begin their long embrace. Eventually their stars will mix, their central black holes will spiral together, and the two will form one vast elliptical galaxy. A new system, calm and resplendent, born from the union of two giants. Astronomers have watched many such mergers unfold in distant space. Telescopes capture galaxies mid-embrace, some with long tidal tails, others tangled in chaotic loops of starlight. One famous example, the Antennae Galaxies, shows two spirals caught in the act of merging, their arms stretched into graceful arcs like the limbs of a dancer mid-spin. Another, the Tadpole Galaxy, trails a glittering stream of stars more than 200,000 light-years long. Each of these cosmic encounters tells the same story, that from collision comes renewal. Despite the drama, these events unfold so slowly that, if you could somehow watch them in real time, they would appear utterly still. A single frame of motion might take 1,000,000 years. Galaxies may collide, but they do so with the patience of glaciers, moving through space in silence. Even when they tear and twist each other's shapes, the result is not destruction, but transformation. The universe has a gentle hand, even in its grandest motions. Over time, these mergers help to sculpt the cosmic landscape. Smaller galaxies are swallowed by larger ones, fueling growth and evolution. Giant ellipticals, the most massive galaxies in the universe, are thought to be the end products of many such mergers. Their smooth, featureless appearance hides a turbulent past, the remnants of countless smaller systems now blended into a single, serene whole. It's a bit like the calm surface of an old tree, whose rings tell a story of storms long weathered. The slow rhythm of these encounters also keeps the universe dynamic. Even today, galaxies continue to find each other across the expanding void, drawn together by the same force that once gathered the first clouds of gas. Every merger reshuffles the stars, redistributes the gas, and sets the stage for new generations of galaxies to grow. Without these collisions, the universe would be far less diverse, a quieter place perhaps, but not nearly as rich. If there's a kind of poetry to all this, it's that even the universe's roughest moments happen in peace. Collisions that last for billions of years don't feel violent, they feel inevitable, almost tender. Gravity doesn't rush, it guides. The galaxies don't crash, they merge, their spirals entwining in slow motion until a new shape is born. It's cosmic choreography, serene, patient, and endlessly creative. So when you look up at the night sky and see the faint smudge of Andromeda, remember that you're seeing not a stranger, but a future partner. Long after we are gone, our galaxy will glide toward hers. the two moving together in a silent embrace that will take billions of years to complete. From that distant dance will rise a new creation, a reminder that, in the universe, even collisions can be beautiful. At the quiet heart of almost every galaxy lies something extraordinary, a black hole, vast and invisible, holding millions or even billions of times the mass of the Sun. It sits in silence, wrapped in gravity so strong that nothing, not even light, can escape. Yet paradoxically, some of the brightest objects in the universe are powered by these very same dark engines. Galaxies, it seems, have learned to keep their most powerful forces hidden at their centres, like a candle burning at the bottom of a well. These colossal black holes didn't appear fully formed. They began as seeds, remnants of the first massive stars, or perhaps as dense clouds of gas that collapsed directly under their own gravity in the earliest galaxies. Each was born small, by cosmic standards, only a few tens or hundreds of thousands of solar masses. But given time and an abundant diet of gas and stars, these seeds grew into the giants we know today. As galaxies evolved, so too did their central black holes. Every major merger, every inflow of gas, sent fresh material spiralling toward the galactic centre. There, the gas formed a glowing, rotating disk, heating up as it fell inward. This disk, called an accretion disk, can shine brighter than all the stars in the host galaxy combined. When this happens, the black hole enters what astronomers call an active phase, and the galaxy becomes an active galactic nucleus, or AGN. During these rare and brilliant seasons, the once dark heart of the galaxy blazes like a beacon. Matter falling toward the black hole compresses and spins, glowing with intense radiation before vanishing past the event horizon. In some cases, twin jets of energy shoot out from the poles of the black hole, stretching for thousands of light years through space. These jets can be so powerful that they outshine entire galaxies, visible across billions of light years as quasars, the universe's brightest lighthouses. Yet these active phases don't last long. Most of the time, a galaxy's central black hole sits quietly, like a dormant volcano. The fuel supply runs out, the bright accretion disk fades, and only the quiet gravitational influence remains. But even in its silence, the black hole still affects its surroundings. Its mere presence shapes the orbits of nearby stars, anchors the galactic centre, and stabilizes the overall structure. The balance between activity and rest is delicate, and it's this rhythm that ties black holes to the life cycles of their galaxies. When a black hole feeds, it doesn't simply grow fatter, it changes its environment. The energy it releases as light, heat, and jets can drive powerful winds through the galaxy, blowing gas outward. Sometimes, this feedback acts like a cosmic thermostat. Too much activity, and the galaxy's gas heats up or gets expelled, suppressing new star formation. Too little, and gas cools, flows inward, and triggers another feeding phase. It's a self-regulating system, where the galaxy and its black hole take turns calming and stirring one another. In massive galaxies, this feedback can be dramatic. The jets from an active nucleus can carve out vast cavities in the surrounding gas, seen in radio waves as huge bubbles extending tens of thousands of light years. In smaller galaxies, the process is gentler, more of a quiet conversation than a storm. Either way, the relationship ensures that galaxies don't form too many stars too quickly, keeping their evolution balanced over cosmic time. This intimate connection between galaxies and their central black holes is one of the most surprising discoveries in modern astronomy. For a long time, scientists assumed the two evolved separately, galaxies making stars, black holes minding their own business in the centre. But observations revealed a striking pattern. The mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's bulge, the dense central region of stars. The bigger the bulge, the bigger the black hole. This relationship, known as the M-sigma relation, suggests that galaxies and black holes grow together, a kind of cosmic co-evolution. Every time a galaxy merges or forms new stars, its central black hole grows alongside it, and every time the black hole erupts with energy, it reshapes the galaxy's ability to form more stars. It's an elegant feedback loop, a quiet partnership written into the universe's blueprint. In some galaxies, these black holes still put on spectacular shows. Quasars, for example, are simply active galaxies caught in their luminous phase. Their light travels billions of years to reach us, a reminder of how energetic the early universe once was. Other galaxies display faint, flickering signs of activity, the last embers of once mighty quasars now fading into dormancy. Even in death, or something close to it, these galactic hearts retain their dignity, glowing softly in the cosmic dark. The process by which black holes grow is astonishingly efficient. As matter falls inward, only a small fraction is swallowed. Most of the energy is radiated away. This efficiency makes accreting black holes some of the most powerful engines in the universe, more efficient than any known physical process, converting a few percent of mass directly into energy. The black hole itself, though, remains silent about the whole affair. It takes in everything, gives back nothing but gravity, and lets the surrounding space tell the story of what's happening within. There's also a strange serenity in their nature. Despite their fearsome reputation, black holes are remarkably stable creatures. Once formed, they persist indefinitely, influencing the cosmos without drama. They don't roar or rage, they wait. Galaxies come and go, stars are born and die, but the black hole at the centre remains, a silent observer of eons. Our own galaxy holds such a presence, Sagittarius a star, a supermassive black hole about 4 million times the mass of the Sun, resting quietly at the Milky Way's centre. Most of the time it slumbers, accreting little material, its glow faint and subdued. But occasionally, when a wandering cloud or star drifts too close, it stirs awake briefly, flickers with energy, and then returns to calm. It is a gentle giant, a sleeping ember in the heart of a spiral. Across the universe, every galaxy tells a variation of this same story. Bursts of brilliance followed by long periods of stillness. The loud seasons of activity shape the cosmos, seeding it with light and heat, while the quiet seasons allow structure and order to return. It's a rhythm as old as time itself, an unending balance between energy and rest, motion and stillness. And so, while the first stars may have brought light to the universe, the first black holes gave it depth. They became the anchors of galaxies, the engines of transformation, the keepers of cosmic balance. From their fiery beginnings to their present tranquility, they remind us that even the darkest objects in the universe can illuminate it in their own way, not through light, but through the gravity that holds everything together. In the end, a galaxy's story is inseparable from the story of its black hole. The two grow, evolve, and rest together, partners in the grand design. And though black holes may spend most of their time in silence, the universe itself still hums softly to their tune, a melody of patience, balance, and quiet power that echoes across the stars. Within every galaxy, amid the quiet hum of starlight and drifting gas, lie the great nurseries of creation, vast cold clouds of molecular hydrogen and dust where new stars are slowly, patiently born. These regions are enormous, spanning dozens or even hundreds of light years, yet they're so faint and cool that they can only be seen in infrared or radio wavelengths. From the outside, they look like soft shadows against brighter backgrounds, dark and featureless. But inside, they are alive with motion, swirling, rippling, collapsing and creating. These molecular clouds are among the most tranquil-looking yet dynamic places in the universe. Their gas is cold, just a few tens of degrees above absolute zero, and dense enough for hydrogen atoms to pair up into molecules. Mixed within are traces of carbon monoxide, dust grains, and complex organic compounds, all drifting together in slow, turbulent patterns. Gravity, magnetic fields, and turbulence dance in delicate balance, keeping the clouds stable until every so often a small patch grows dense enough to collapse under its own weight. Star formation begins in these quiet collapses. The process is neither sudden nor simple. It's a careful negotiation between gravity pulling inward and pressure pushing outward. Turbulence inside the cloud creates knots and filaments where matter gathers, and over time, some of those knots become just dense enough for gravity to win. Once collapse begins, the gas at the centre heats up as it falls inward, forming a small hot core, the earliest stage of a new star. You could think of these clouds as the universe's most patient maternity wards. Nothing happens quickly here. A single star might take millions of years to form from start to finish. Gravity, after all, works best when given time. It nudges, it persuades, it coaxes the gas inward, never forcing, only guiding. And while this process unfolds at a pace almost unimaginable to us, it happens all across the galaxy, in hundreds of thousands of places at once. The universe has perfected the art of slow, steady creation. Astronomers can describe the overall rhythm of this process with what's known as an empirical rule, the Kennicutt-Schmidt law. Despite the complicated physics inside molecular clouds, this law says something surprisingly simple. The rate at which stars form in a galaxy depends on how much gas it has. More gas means more star formation. Less gas means fewer stars. It's as though galaxies obey a quiet universal tempo, each one forming stars in proportion to its available fuel. Some galaxies hum along at a steady pace, while others experience brief crescendos, starbursting into brilliance before calming down again. Within each molecular cloud, the process repeats at many scales. Small clouds may form just a handful of stars. Larger ones may create entire clusters, with thousands of newborn suns emerging together. These clusters often remain bound by gravity for millions of years, their members drifting slowly apart over time. Many of the stars you see in the night sky began their lives this way, siblings born in the same cloud, long since separated but still carrying the chemical fingerprints of their shared origin. The role of dust in this process is quietly crucial. Tiny grains, mostly made of carbon, silicates and ice, provide surfaces for molecules to form, and they shield the interiors of clouds from harsh radiation. Without dust, molecular hydrogen would be destroyed by ultraviolet light, and star formation would stall. Dust also absorbs and re-emits light, allowing clouds to cool efficiently, which is necessary for gravity to keep pulling the gas inward. It's a subtle but vital balancing act. Too warm, and the cloud disperses. Too cool, and the collapse accelerates. Somehow, the universe finds the middle ground. Once a dense core forms within the cloud, it continues to collapse until its central temperature rises high enough for nuclear fusion to begin. At that moment, a star is born. Around it, a disk of leftover gas and dust often forms, the raw material for planets, moons, and comets. The newborn star shines, first faintly, then more brightly, pushing back against the surrounding cloud with its radiation and winds. Nearby regions may collapse in response, triggering more star formation in a self-sustaining chain of creation. These feedback effects, the winds, radiation, and supernovae from young stars, act both as midwives and regulators. They can compress nearby gas, encouraging more stars to form, or they can disperse it, halting formation for a time. In this way, galaxies maintain a steady rhythm of birth and rest, creation and pause. It's a process both self-perpetuating and self-limiting, ensuring that no galaxy burns through its gas too quickly. Star formation also has its own demographics. Not all stars are born equal. Most form small and faint, like red dwarfs, that will quietly burn for trillions of years. A smaller number become suns like our own, living for billions of years before gently fading, and a precious few are born massive, bright, hot, and short-lived, burning their fuel in mere millions of years before ending in spectacular supernovae. Together, these populations shape the character of each galaxy. Young blue galaxies are rich in massive short-lived stars, while older, red galaxies are home mostly to smaller, long-lived ones. Astronomers describe this distribution as the initial mass function, a statistical rule that nature seems to follow with remarkable consistency. Wherever stars form, from the Milky Way to distant galaxies billions of light-years away, the same basic pattern appears. It's as though the universe, despite all its variety, prefers to compose its music in a familiar key. What's astonishing is how stable and self-regulating this entire process is. Even though galaxies evolve, collide, and lose gas over time, the overall pattern of star formation remains balanced. It's not chaotic, it's rhythmic. The universe builds itself carefully, in measured steps, ensuring that its light never flickers out too soon. If you could drift inside one of these star-forming clouds, the view would be ethereal. Dense curtains of dust would block most starlight, while faint ghostly glows of infrared radiation would shimmer through the haze. You'd see long filaments winding through the cloud, like rivers of darkness flowing through dim light. Here and there, small pockets would gleam where new stars are beginning to emerge, surrounded by disks of warm dust. In time, these will clear their surroundings, sending tendrils of gas streaming outward like cosmic sighs. And yet, despite the stillness, everything within is in motion. Turbulent eddies churn unseen, magnetic fields twist and stretch, and gravity continues its quiet persuasion. There's no rush, no urgency. The universe has all the time it needs. In the end, molecular clouds are where the universe renews itself, over and over again. Every star that ever shone, every planet that ever formed, began as a wisp of gas in one of these great nurseries. The process is ancient, constant, and deeply peaceful. A reminder that creation doesn't always roar. Sometimes it whispers. If galaxies are the grand cities of the cosmos, then these molecular clouds are their neighborhoods of birth, humming softly with quiet purpose. They are the calm factories of light, transforming simple gas and dust into the stars that will illuminate the universe for eons to come. And in their slow, patient way, they remind us that even in the coldest and darkest places, the cosmos never stops making something new. In astronomy, the word metal means something very different from what it does on Earth. To an astronomer, almost every element heavier than hydrogen and helium counts as a metal, from carbon and oxygen to silicon, iron and gold. It's an unglamorous definition, but a revealing one, because it reminds us how simple the early universe really was. In the beginning, there were no metals at all. Only the first stars could make them, and through their fiery lives and explosive deaths, they slowly turned the universe from a dull canvas of hydrogen and helium into the colourful, chemically rich cosmos we see today. Metals are the fingerprints of stellar generations. Each new star carries the chemical inheritance of those that came before it. The first stars, enormous and short-lived, fused the lightest elements into heavier ones in their cores, elements like carbon, oxygen, and iron. When they died in supernovae, they scattered these materials into space, enriching the gas clouds around them. Later generations of stars formed from that enriched gas, adding their own elements to the mix when they eventually met their ends. Over billions of years, this process of enrichment, of death-feeding life, turned the cosmos into a chemical mosaic, one supernova at a time. This slow accumulation of metals changed everything. With each generation, the gas that formed new stars became more complex. Metal atoms and molecules made it easier for gas to cool, which meant that stars could form in smaller, denser regions. Dust grains, tiny specks made from heavier elements, began to appear too, providing surfaces where molecules could form and shielding fragile gas clouds from intense radiation. With dust came chemistry, with chemistry came planets, and with planets came the potential for life. You could think of it as the universe slowly learning to paint. In its earliest age, the palette was limited to just two colours, hydrogen blue and helium white. But with time and with stars, new pigments appeared. The crimson of carbon, the silver of oxygen, the rust of iron and the glitter of silicon. The galaxies began to glow not just with light, but with personality. Each one's spectrum, the unique pattern of light it emits, became a record of its chemical history. Metals may make up only a small fraction of a galaxy's mass, but their influence is enormous. They determine how bright and long stars can shine, how planets can form, and how light travels through space. In regions rich with dust, starlight is softened and scattered, creating the golden haze of nebulae and the reddish tinge of distant sunsets. Without dust, light would blaze harsh and unfiltered. With it, the cosmos gains depth, contrast, and texture. It's as if the universe draped itself in fine curtains, letting its light fall through gently woven threads. The formation of these dust grains is a quiet kind of alchemy. In the outer layers of dying stars, where temperatures and pressures are just right, atoms condense into tiny solid particles. These grains are microscopic, often smaller than a wavelength of light, yet they fill galaxies in unimaginable numbers. When supernovae explode, they blast some of this dust outward, seeding interstellar space with new material. Much of it is destroyed in shocks and collisions, but some survives, drifting between stars, gathering into new clouds, and beginning the cycle again. This cycle of creation, destruction, and renewal gives galaxies their chemical richness. Over billions of years, the amount of metal in a galaxy slowly increases, a measure astronomers call metallicity. Younger galaxies in the early universe tend to be poor in metals, while older galaxies like our own Milky Way are more enriched. Even within a single galaxy, metallicity isn't uniform. The cores, where star formation has been most active, are richer, while the outer regions remain comparatively pristine. It's as though each galaxy has aged from the inside out, building its complexity one stellar generation at a time. Metals also influence the lives of stars themselves. A star rich in metals cools more efficiently, producing a softer, redder light. One poor in metals burns hotter and bluer. The different shapes not only how stars look, but how long they live. In this way, chemistry becomes destiny. A star's metallicity determines its colour, its lifespan, and even the kind of supernova it will one day produce. Every glittering point of light in the night sky is, in its own way, a chemical statement, an essay written in photons. On a larger scale, metals and dust guide how galaxies evolve. Dust absorbs ultraviolet and visible light, re-emitting it as infrared radiation, which helps cool the surrounding gas. This cooling allows new generations of stars to form in regions that would otherwise remain too warm. At the same time, the winds from massive stars and the shock waves from supernovae redistribute these metals throughout the galaxy, spreading them far from where they were made. Galaxies breathe in and out chemically, enriching, mixing, and redistributing their ingredients with every cosmic heartbeat. The connection between stars, dust and light is visible everywhere. When we look at images from telescopes, the golden hues of old stars, the blue of young clusters, and the rosy pinks of glowing hydrogen clouds are all signatures of chemistry at work. Even the dark lanes that cut across spiral galaxies, those dusty streaks that look like shadows, are regions rich with heavy elements, blocking and scattering starlight as they cradle the next generation of stars within. Without those shadows, galaxies would lose their texture and mystery. Our own existence is part of this story too. The calcium in our bones, the oxygen we breathe, the iron in our blood, all were forged in ancient stars and scattered across space by their deaths. The dust that once drifted between stars eventually gathered into the cloud that formed our sun and planets. When you look up at the night sky, you are quite literally looking at your ancestors. Every atom of your body was once part of a star that lived, burned and died billions of years ago. It's easy to forget how much of the universe's beauty is owed to these trace elements, this cosmic seasoning sprinkled lightly across the galaxies. Without them, stars would burn too hot and too short, planets would never coalesce, and light would travel through space uncoloured, like a world without sunsets. Metals and dust give the cosmos its richness, not only in composition, but in expression. If you could drift through a galaxy and watch its light change as you pass through dusty regions, you'd see it shift gently, from white to gold to red, as though filtered through layers of fine silk. The dust doesn't block the light entirely, it softens it, turning brilliance into warmth. The effect is both scientific and poetic, the universe painting with chemistry, layering its radiance with the faintest touch of shadow. In the end, metals and dust are the universe's quiet artists. They don't roar or blaze like supernovae, but they shape what those explosions leave behind. They give galaxies their colour, their complexity, and their potential for life. Every star, planet, and living being carries their signature, and as starlight filters through those fine cosmic curtains, the universe reveals not just its structure, but its soul, a masterpiece drawn slowly, one atom at a time. Scattered across the vast darkness of the cosmos are countless small, faint galaxies, quiet, unassuming, and easy to overlook. They lack the grand spirals and sweeping arms of their larger cousins, yet they vastly outnumber them. For every majestic galaxy like the Milky Way, there are dozens, perhaps hundreds, of tiny companions drifting nearby. These are the dwarf galaxies, the little lanterns of the universe, glowing softly at the edges of the cosmic web. At first glance, dwarfs might seem unimportant compared to the great galactic giants, but in truth, they are the backbone of cosmic history. They are the first galaxies that ever formed, the original building blocks from which larger ones were assembled. They are fragile, yes, but in their simplicity lies the story of how galaxies came to be. A typical dwarf galaxy might hold only a few million stars, a mere flicker compared to the hundreds of billions in the Milky Way. Some are even smaller, with only a few thousand stars, scattered like a sparse constellation frozen in place. Their low mass makes them vulnerable to every cosmic gust of wind. A nearby supernova can blow out much of their gas, halting star formation for millions of years. A close encounter with a larger galaxy can strip away their outer layers, leaving them faint and weary. They are, in a sense, the delicate flowers of the cosmic garden, easily disturbed, yet remarkably persistent. Because they are so small, dwarf galaxies react dramatically to feedback. When a burst of star formation occurs, the radiation and stellar winds from those newborn stars can heat and expel gas, effectively shutting down further star formation. It's a bit like trying to light a candle in a breeze. the faintest puff can snuff it out. And yet, given time, the gas can cool and fall back in, reigniting the cycle. In this way, dwarfs flicker through their lives, alternating between bright phases of creation and long, quiet intervals of rest. Many dwarves live as satellites around larger galaxies. The Milky Way, for instance, has at least 50 known companions, though astronomers suspect there are many more hiding in the shadows. Some, like the large and small Magellanic Clouds, are visible to the naked eye in the southern hemisphere, glowing patches of light that orbit our galaxy in a slow, graceful dance. Others are so faint that they were only discovered in recent decades, their stars barely distinguishable from the background. Living near a giant galaxy isn't easy. The gravitational tides from a massive neighbour can stretch and distort a dwarf, pulling stars away in long streams that wrap around the parent system. Over time, many dwarfs are completely absorbed, their stars becoming part of the larger galaxy's halo. The Milky Way has consumed many such companions throughout its history, quietly growing by swallowing these smaller systems whole. Yet even in their disappearance, dwarfs contribute, feeding their stars gas and metals into the galactic ecosystem. Some dwarfs, however, manage to survive for billions of years, quietly orbiting in peace. Their shapes vary widely. Some are irregular, messy collections of gas and stars with no clear structure. Others are smooth, spheroidal clouds of ancient stars, their gas long gone. The irregular dwarfs tend to be still-forming stars, while the spheroidals are old and quiescent, their star formation quenched long ago. Environment plays a big role in this difference. Dwarfs close to large galaxies often lose their gas early, while those in isolation can keep forming stars at their own gentle pace. Despite their modest size, dwarf galaxies have much to teach us. Because they are simple systems, their internal processes are easier to study, revealing the basic physics of star formation, feedback, and chemical enrichment. They act as natural laboratories, miniature versions of the cosmos where we can see its rules played out in smaller, slower ways. By observing dwarfs, astronomers learn how galaxies grow, how they recycle gas, and how they balance the competing forces of gravity and energy. Dwarfs are also valuable fossils of the early universe. Some of them formed their stars more than 12 billion years ago, and have changed little since. These ancient dwarfs preserve a record of what conditions were like when galaxies first emerged, their stars carrying the chemical fingerprints of a universe still learning to make heavy elements. Studying them is like reading an early draft of the universe's autobiography, written in starlight and silence. Even the smallest dwarfs can hold secrets about dark matter. Because they're so dominated by it, with far more mass in dark matter than in visible stars, they serve as excellent testbeds for understanding this mysterious substance. Their slow-moving stars trace the gravitational pull of their dark halos, allowing astronomers to map the invisible with remarkable precision. Some of the strongest evidence for dark matter's existence comes from these humble galaxies that seem, at first glance, too faint to matter at all. The diversity of dwarf galaxies is part of their charm. Some are compact and dense, glowing like tiny pearls. Others are diffuse and ghostly, so faint that their starlight barely reaches us. A few, called ultra-faint dwarves, are so dim they challenge the limits of our telescopes, containing only a few thousand stars scattered across vast stretches of space. Yet these tiny systems are among the oldest and most pristine in the universe. Time capsules from an era when galaxies were still forming their first stars. In recent years, astronomers have discovered that even the smallest dwarfs can host surprisingly complex behaviours. Some have rotating disks, others show signs of past mergers, and many have intricate patterns of star formation and chemical enrichment. It's a reminder that, Even in miniature, galaxies are full of surprises. The universe does not play favourites. It gives every galaxy, no matter its size, a chance to shine. If you could look at a dwarf galaxy up close, you might find it beautiful in its own quiet way. Its stars would be scattered sparsely across a velvet backdrop, their combined light soft and uneven. Here and there, faint pink glows would mark pockets of new star formation, while older, redder stars would drift like embers. There's a fragility to these systems, a sense that a single strong wind could scatter them, yet they endure, century after century, epoch after epoch. Their beauty lies in subtlety. While massive galaxies dazzle with grandeur, dwarf galaxies whisper their stories. They remind us that most of the universe is made not of the spectacular, but of the small, the overlooked, and the patient. Their faint light has been shining, unbothered, for billions of years, carrying the quiet history of the cosmos. And in their persistence, there's something profoundly hopeful. Even the faintest galaxies, fragile and often forgotten, contribute to the universe's vast tapestry. They are the quiet workers, the starlight flickering in the distance, the fireflies of the cosmic night. Together, their collective glow fills the darkness, proving that even the smallest lights can help illuminate the universe. Galaxies are not isolated wanderers. They live in communities, bound together by gravity, interacting through gentle tugs and occasional close encounters. These cosmic neighbourhoods come in all sizes, from small groups like the one our Milky Way belongs to colossal clusters containing thousands of galaxies packed into regions only a few million light-years across. And just like in human cities, the neighbourhood shapes its residents. Where a galaxy lives influences how it looks, how it behaves, and how long it keeps forming stars. Astronomers call this the morphology-density relation, a calm and elegant way of saying that galaxies in crowded areas tend to look different from those in quieter regions. In the dense centres of galaxy clusters, ellipticals dominate, round, smooth, and largely composed of older stars. Out on the outskirts, in the cosmic suburbs, spirals flourish, their graceful arms still rich with gas and ongoing star formation. Between these two extremes lies a gradient of galactic lifestyles, each moulded by its surroundings. The reason environment matters is because space, while vast, is not empty. Even in the darkness between galaxies, there's a thin haze of hot gas, the intra-cluster medium, and the gravitational fields of neighbouring systems are always at work. When galaxies move through dense regions, they feel this medium pushing against them, stripping away their own gas in a process called ram pressure stripping. It's not unlike driving through a strong wind. The faster the motion, the greater the pressure. Over time, this cosmic headwind can peel away a galaxy's gas, leaving it unable to form new stars. What remains is a quieter, redder system, an elliptical or lenticular galaxy, calm and mature. In the bustling city centres of clusters, interactions between galaxies are frequent. They orbit one another in tight spaces, their halos overlapping, their motions tugging on each other's stars. These encounters can stir up the delicate structure of a spiral, heating its disk and redistributing its stars until the elegant spiral arms fade into a smoother, more spheroidal shape. Collisions and mergers are also more common here, turning pairs of smaller galaxies into single, more massive ellipticals. The cluster core, then, is a place where galaxies grow up fast, losing their youthful gas and settling into old age under the weight of gravity and proximity. Spiral galaxies, by contrast, prefer the peace of the outskirts. In these less crowded regions, there's more cold gas available, fewer disruptive encounters, and space to maintain those fragile disks. The spirals can keep spinning gracefully, forming stars at a leisurely pace, and preserving their structure for billions of years. The Milky Way, for example, resides in such a calm neighbourhood, part of a small group rather than a crowded cluster. Here, the environment allows it to keep its spiral arms intact and its star formation gently ongoing. This pattern, spirals on the fringes, ellipticals in the centre, is not a rule without exceptions, but a tendency shaped by nature and nurture working together. The nature side is what a galaxy is born with, its mass, its angular momentum, its dark matter halo. The nurture side is what happens after birth, the interactions, mergers and environment that sculpt it over time. Together, these forces weave the diversity of galactic forms that populate the universe. In the heart of galaxy clusters, where thousands of systems orbit within a shared gravitational well, the pace of galactic life is intense. The intergalactic gas there can reach tens of millions of degrees, glowing in the X-rays. As galaxies plunge through it, they experience a fierce drag, losing their star-forming material in long, trailing plumes. Some galaxies show vivid evidence of this, bright blue tails where gas is stripped and compressed into knots of new stars like sparks flying from a cosmic wind tunnel. Eventually, these galaxies run out of fuel, their star formation fading as they drift deeper into the cluster. Elliptical galaxies, the elder citizens of this cosmic metropolis, dominate the centre. They are massive, smooth and red, their stars long past the flush of youth. Many of them were formed from the mergers of smaller galaxies, their chaotic pasts smoothed over into tranquil uniformity. Inside, stars move in all directions, creating a rounded, featureless glow. These galaxies are efficient recyclers, turning the energy of past collisions into stable equilibrium. If spiral galaxies are the lively suburbs, ellipticals are the graceful old cities, dense with history and quiet dignity. Between these two extremes lie transitional forms, lenticular galaxies, systems that resemble spirals stripped of their youth. They have disks but no prominent arms, their gas largely gone, their star formation quenched. They are the suburban commuters of the galactic world, caught between the freedom of the outskirts and the formality of the cluster centre. Lenticulars remind us that galaxy evolution is rarely abrupt. It's a continuum shaped by gradual environmental influence. In groups, smaller associations of just a few dozen galaxies, the story is gentler but still rich with interaction. Galaxies and groups experience tidal forces and occasional mergers, but with more breathing room. These groups act as cosmic training grounds. Galaxies evolve, grow, and sometimes collide before eventually falling into larger clusters. Our own local group, containing the Milky Way, Andromeda, and dozens of dwarfs, is a quiet example of this. The Milky Way and Andromeda are slowly drawing together, destined to merge billions of years from now, forming a future elliptical of their own. The beauty of studying environment is that it reveals how dynamic the universe truly is. Galaxies are not static objects, they are social creatures, constantly influenced by their surroundings. Even isolated galaxies can feel the pull of nearby structures, the slow drift of cosmic filaments guiding their growth. In the densest clusters, where gravity binds thousands together, the collective behaviour becomes almost ecological, a balance of creation and quenching, competition and cooperation. Astronomers can even map these patterns statistically. When plotting galaxies by their morphology and their local density, a clear trend emerges. The denser the environment, the redder and rounder the galaxies become. This isn't just coincidence. It's the imprint of billions of years of gravitational interactions, of gas stripped, stars scattered, and structures reshaped. The universe, through its quiet laws, has built something akin to urban planning, with elegant spirals out in the quiet suburbs and stately ellipticals filling the bustling downtowns of galaxy clusters. And yet, amid all this order, there's still room for personality. Some spirals manage to survive deep within clusters, protected by favourable orbits or unusually stable halos. Some ellipticals linger on the outskirts, relics of earlier mergers. Like any city, the universe's architecture isn't perfect or uniform. It's full of exceptions and stories. If you could drift through a galaxy cluster, the view would be magnificent. At its core, enormous ellipticals would glow like amber lanterns, surrounded by smaller, fainter companions. Streams of gas would wind between them, shimmering faintly in X-ray light. Out toward the edges, delicate spirals would spin quietly, their blue arms filled with young stars. The whole scene would feel like a living city, busy, luminous, and constantly reshaping itself. Ultimately, the environment's role in shaping galaxies is a story of quiet persistence rather than sudden change. Over billions of years, the slow tides of gravity, the push of hot gas, and the cumulative effects of encounters mould each system into its final form. The universe, as it turns out, is both artist and sculptor, using not chisel or brush, but the patient forces of time and proximity. Galaxies are what they are not just because of how they were born, but because of where they have lived. Each one carries the memory of its neighbourhood in its shape, its colour, and its light. A cosmic address written in stars. Galaxies, like living things, have lifespans. They are born bright and restless, filled with gas and star formation, and then, over billions of years, they begin to slow down. Their brilliant blue hues fade into gold and then into soft crimson. The nebulae quiet, the gas thins, and one by one the lights of creation flicker out. What remains is not death in the dramatic sense, but a serene retirement. A galaxy that has simply decided to stop making new stars. Astronomers call this process quenching, and it can happen in a few different ways. Some galaxies simply run out of fuel. After billions of years of converting gas into stars, there's not much left to work with. The cold reservoirs that once filled the disk are gone, heated or used up, leaving the galaxy with little material to feed the next generation. Others still have gas but can't use it. Something prevents it from cooling and collapsing. Perhaps the heat from surrounding plasma, or the energy pumped in by an active black hole at the galaxy's core. Whatever the reason, the result is the same. The star-making machinery shuts down, and the galaxy begins its long, graceful fade into stillness. You could think of this as cosmic exhaustion versus cosmic prevention. In some galaxies, the gas supply is simply depleted, an honest case of running out of fuel. In others, the gas remains, but is kept too warm or too disturbed to condense into new stars. This strangulation, as astronomers rather dramatically call it, happens when a galaxy can no longer draw in fresh, cold gas from its surroundings. The old fuel is gradually used up, but nothing new replaces it. It's the galactic equivalent of living off your savings until there's nothing left in the account. Heating, on the other hand, is the universe's way of keeping a galaxy awake, and ironically, that can stop star formation too. In large clusters, the intergalactic gas can be millions of degrees hot. Any cool gas trying to fall into a galaxy is instantly reheated, unable to settle or condense. Even within galaxies themselves, active black holes and supernova explosions can inject enough energy to keep the surrounding gas too warm and turbulent to form stars. It's as if the universe, at some point, decided it was time to dim the lights and told the galaxies to take a well-earned rest. Feedback plays a big role here. When a galaxy's central black hole is active, it can release enormous amounts of energy in the form of radiation and jets. That energy ripples through the galaxy, heating gas and driving it outward. This feedback acts like a thermostat, too much activity, and the black hole shuts off its own fuel supply by blowing it away. Too little, and gas begins to fall back in, reigniting the cycle. Over time, this delicate balance leads to stability. A galaxy that no longer burns bright with new stars but instead glows steadily with the light of old ones. How a galaxy quenches can depend on its size and environment. Massive galaxies tend to stop forming stars from the inside out. Their centers, packed with dense gas and active black holes, heat up first, halting star formation in the core while the outskirts continue for a while longer. The result is a galaxy with an aged red heart surrounded by a fading bluer disk, a slow and graceful decline rather than a sudden end. Smaller galaxies, especially those in crowded neighborhoods, often experience the opposite, outside-in quenching. Stripped of their outer gas by the hot medium or tidal forces of a larger neighbor, their star formation dies first on the edges, shrinking inward like a candle burning from both ends. Over cosmic time, this transition reshapes the character of the universe. In the early epochs, galaxies were vibrant and blue, full of gas and creation. But as billions of years passed, many settled into a quieter phase, becoming redder and smoother. Today, most of the light we see in the cosmos comes from old stars, ancient suns that have been shining for 10 billion years or more. The age of frantic star-making has given way to one of graceful maturity. There's a certain beauty in that stillness. When a galaxy goes quiet, it doesn't fade into obscurity. It glows in a softer light, its population of older stars bathing it in warm golden tones. These red and dead galaxies, as astronomers affectionately call them, are some of the most elegant objects in the sky. Their shapes are smooth, their motions calm, their light steady. They've traded the chaos of youth for the dignity of age. Sometimes galaxies are coaxed into quiescence by their surroundings. In dense clusters, the hot intracluster gas strips away a galaxy's cold reserves, while gravitational tides distort its structure. This environmental quenching can happen surprisingly quickly, turning once spiraling star-forming galaxies into featureless ellipticals in only a few 100 million years. It's as if living in the cosmic city center accelerates aging. Too much noise, too much heat, too many interactions. Meanwhile, galaxies in quieter outskirts can remain young and active much longer, forming stars at a leisurely pace in the galactic suburbs. Even within a single galaxy, the process is far from uniform. Some pockets of gas remain active long after most of the system has quieted down. A few new stars might continue to flicker into existence, adding the occasional spark of youth to an otherwise mature population. These holdouts are the last embers of star formation, reminders that even in retirement, a galaxy can still surprise you. Astronomers study this decline through the colour of galaxies. Blue means young, full of massive hot stars that burn brightly and live briefly. Red means old, populated by cooler, longer-lived stars that have aged gracefully. Between the two lies the Green Valley, a transitional zone where galaxies are in the process of shutting down star formation. The Green Valley is where galaxies go to catch their breath, the intermission between the bright act of creation and the soft finale of endurance. And yet, even this finale isn't the end of the story. Quenched galaxies can sometimes awaken again. A merger, or a sudden influx of cold gas, can rekindle star formation, giving rise to new bursts of light. These rejuvenated galaxies are rare, but they show that the universe never completely closes the door on renewal. Like an old library getting a fresh set of books, they remind us that cosmic quiet doesn't always mean permanent silence. Still, for most galaxies, quenching marks a lasting peace. The lights dim, the gas settles, and time stretches on. The galaxy becomes a monument to its own history, a glowing archive of the stars it has already made. In their tranquility, these galaxies radiate a different kind of beauty. Not the brilliance of youth, but the warmth of endurance. If the universe could speak, it might say that it knows when enough is enough. There comes a time to stop building and simply shine with what has been made. Galaxies, it seems, understand that too. They spend their early years in bright, restless creation, but eventually they learn the art of stillness, and in that quiet they find grace. Among the billions of galaxies scattered through the universe, one holds a special place for us, not because it is rare or extraordinary, but because it is home. The Milky Way, our quiet spiral of starlight, stretches across the night sky like a soft band of mist, a river of stars flowing endlessly overhead. From afar it would look like a graceful whirlpool of light, bright at the centre, thin and delicate at the edges, its arms curling outward in serene symmetry. Yet its beauty is more than skin deep. Every swirl and shimmer carries the story of 13 billion years of cosmic craftsmanship. The Milky Way began humbly, as most galaxies did. In the early universe, small clouds of dark matter and gas clumped together under gravity, merging and growing over time. These were the first fragments of what would one day become our galaxy. Each merger added new material, fresh gas for stars, and stars themselves from the smaller systems being absorbed. This slow, hierarchical assembly built the Milky Way's halo, a vast, faint sphere of ancient stars and dark matter that still surrounds us today. Some of the oldest stars in existence live out there in quiet isolation, their chemical fingerprints preserving memories of a time when the universe was still young. As more matter flowed inward, the Milky Way began to organize itself. The gas, drawn by gravity yet guided by angular momentum, started to flatten and spin, forming the beginnings of a disk. Over hundreds of millions of years, that disk grew stable, cooling and rotating with graceful precision. In it, waves of star formation swept through, giving rise to the first spiral arms, glowing trails of young blue stars that wound slowly around the centre. These arms were not permanent structures, but patterns, waves moving through the galactic disk, compressing gas and igniting new generations of stars as they passed. At the heart of the Milky Way, a small bulge of older stars began to take shape, dense and golden, anchored by gravity's pull. Within that bulge, a bar of stars formed over time, stretching across the core like a luminous bridge. This bar acts as a cosmic engine, funneling gas toward the centre where it fuels both new star formation and the quiet feeding of the galaxy's central black hole. That black hole, known as Sagittarius A star, is about 4 million times the mass of the Sun, not large by cosmic standards, but perfectly content in its role. Most of the time, it rests in silence, accreting only a trickle of gas. Occasionally it stirs, flickering briefly in X-rays before returning to calm. It is the Milky Way's hidden heart, invisible yet essential. The process that built our galaxy was anything but smooth. Over billions of years, the Milky Way endured many encounters, small galaxies drawn in and torn apart, their stars scattered like seeds into the halo. Astronomers can still trace the remnants of these mergers today. Streams of stars, faint but distinct, arc across the sky like the ghostly trails of past collisions. Each one tells a story of a smaller companion that once existed, a dwarf galaxy that ventured too close and was absorbed into something larger. Through these encounters, the Milky Way grew stronger, more massive and more structured, each merger a gentle addition to its character. Even now, our galaxy is not alone. It lives in a modest community known as the Local Group, alongside its nearest large neighbour, the Andromeda Galaxy, and a host of smaller companions. The Large and Small Magellanic Clouds, visible from the southern hemisphere, are two of its most charming satellites, irregular, youthful galaxies orbiting us in a slow cosmic dance. Streams of gas connect them to the Milky Way, shaped by tidal forces that pull and stretch their forms. Over time, they too will likely be drawn in completely, becoming part of our galaxy's growing halo. Farther out, dozens of faint dwarf galaxies circle the Milky Way, each a collection of stars and dark matter, barely held together by gravity. Some are ancient fossils, their star formation long finished. Others are still making stars in small bursts. These companions remind us that our galaxy's growth is ongoing. The Milky Way is not a static object, but a living structure, always changing, always balancing creation and absorption, always in quiet motion. Our galaxy's disk, where we live, is about 100,000 light-years across and a few thousand light-years thick. It contains hundreds of billions of stars, billions of planets, and untold clouds of dust and gas. The Sun, along with all its planets, orbits the galactic centre once every 250 million years, moving through spiral arms and open space in a long, slow journey. In all that time, the Milky Way itself continues to evolve, forming stars in its spiral arms, enriching its gas with metals, and gradually transforming its light from blue to gold. When astronomers look closely, they can read the layers of the Milky Way like pages in a history book. The thin disk, rich in younger stars, represents the more recent past, the era of steady, organised star formation. The thick disk, filled with older, redder stars, holds the record of ancient mergers and early turbulence, and the halo, a vast diffuse envelope of stars extending far beyond the visible disk, tells of the galaxy's earliest days, when smaller fragments first came together to form its foundations. Together, these components create a cosmic autobiography written in starlight. In its calm maturity, the Milky Way is a balanced and steady system. It still forms stars, but not recklessly. The gas that feeds new stellar generations flows inward slowly, recycled through supernovae and interstellar winds. Its black hole sleeps, its structure holds, and its arms continue their gentle rotation. Yet even this quiet equilibrium will not last forever. In roughly 4 billion years, our galaxy will meet its twin, Andromeda, in a slow-motion merger that will reshape both into something new. Andromeda is now about 2.5 million light-years away, but the pull between our galaxies is irresistible. They are on a collision course, though collision might not be the right word. When they meet, their stars will mostly pass by one another without ever touching. Their shapes will distort, their spiral arms will twist and merge, and over a few billion years they will settle into a single, massive elliptical galaxy, sometimes whimsically dubbed Milkomeda. It will shine more softly, its spiral grace replaced by a tranquil glow, but its history, and ours, will live on in the orbits of its stars. In the meantime, the Milky Way continues its slow evolution, unhurried and serene. Its spiral arms wind patiently through the dark, nurturing new stars while old ones fade into memory. Its satellites orbit quietly, its centre hums faintly with unseen energy, and its disk drifts through space, a vast rotating sanctuary of light. From our perspective here on one of its minor arms, it's easy to forget the grandeur of what we're part of. Every star we see in the night sky, every faint glow on a clear summer evening, is a tiny piece of this enormous structure, our shared cosmic home. The Milky Way is not just a galaxy among many. It is the story of our origins, the setting of every sunrise, the silent witness to everything humanity has ever known. And though it was built by collisions, enriched by dust, and guided by gravity's hand, it carries itself now with quiet composure. It is an elder galaxy, still graceful, still alive, still spinning softly through the universe. When you look up and see that faint band of light stretching across the sky, you are looking into your own history, the long, gentle story of the galaxy that made us, still writing itself, one slow turn at a time. When we look up at the night sky, we're not just looking outward, we are looking backward. Every point of light, every faint smudge or distant glow, carries with it the memory of when that light first began its journey. The stars of the Milky Way show us the recent past, mere thousands of years old, but the galaxies beyond stretch our vision deeper in time. The farther we look, the older the universe becomes. With the right tools, we can watch galaxies as they were billions of years ago, just beginning to form their first stars. The sky is not only a view of space, it is a living archive of history. Telescopes are our time machines. They work through one simple truth: light takes time to travel. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago, long before our own sun was born. This isn't a metaphor, it's direct observation. In that faint, red-shifted glow, we are seeing the universe as it truly was when it was young, crowded with new galaxies, still glowing with the after-effects of cosmic dawn. Modern telescopes orbiting far above Earth's atmosphere have opened this window wider than ever before. The Hubble Space Telescope gave us some of the deepest images in history, small patches of sky where thousands of ancient galaxies can be seen, each one a whisper from a different era. Those famous deep-field images revealed that even the darkest parts of the sky are full of galaxies, too faint for human eyes to see without patient observation. The James Webb Space Telescope has gone further still, its infrared vision piercing the veil of cosmic dust and revealing galaxies that formed just a few 100 million years after the Big Bang. In its gold-mirrored gaze, we glimpse the universe when it was still an infant. Chaotic, brilliant and busy. Each wavelength of light tells a different story. The visible spectrum shows us stars, the soft blues and yellows of starlight we can see with our eyes. Infrared light, with its longer wavelengths, penetrates dust and reveals the cooler structures hidden within. The gas clouds where stars are born and the distant galaxies whose light has been stretched by cosmic expansion. Ultraviolet and X-ray telescopes trace the high-energy processes, the glow of hot gas, the fury of supernovae, and the feeding of black holes. Even radio waves, invisible and quiet, unveil enormous structures of cold hydrogen and magnetic fields stretching between galaxies. When combined, these views form a layered picture, a cosmic portrait painted in many colours, most of them invisible to the human eye. Astronomers translate these wavelengths into false-colour images so that we can see them, not to deceive, but to reveal. The red and gold hues of nebulae, the blues of spiral arms, the violets of distant quasars, all are part of this symphony of light, each wavelength singing a note from a different part of the universe's history. But telescopes can only observe what light allows. To truly understand how galaxies form and evolve, astronomers also turn to a different kind of instrument, one that doesn't collect light, but simulates it. Inside vast supercomputers, they recreate miniature universes, starting from the conditions just after the Big Bang and letting gravity, gas and physics run their course. These simulations are like time-lapse experiments on a cosmic scale, condensing billions of years of evolution into a few weeks or months of computation. The results are astonishingly lifelike. In the best simulations, galaxies form, merge, and spin just as we observe them in reality. Clusters of galaxies emerge at the intersections of the cosmic web. Filaments stretch across virtual space, and feedback from stars and black holes sculpts the surrounding gas. These digital universes help scientists test their theories. Change one parameter, and you can see how the universe might have looked under different physical rules. They bridge the gap between observation and understanding, giving us a way to ask why the cosmos looks the way it does. Simulations like Illustra's, Eagle, and TNG-50 have become laboratories of the unseen. They allow astronomers to trace the histories of millions of virtual galaxies, following how they gain and lose mass, how they form stars, and how feedback processes shape them over time. What's remarkable is how closely these computer-generated universes resemble our own. The same filaments, the same clustering, the same diversity of shapes appear, suggesting that our understanding of cosmic evolution, while still incomplete, is fundamentally sound. Even so, there are mysteries. Simulations help expose the gaps in our knowledge, where dark matter's exact nature remains elusive, or where star formation behaves differently than expected. In this way, virtual universes are more than models. They're tools for humility, reminding us how much there is left to learn. Every time a telescope surprises us with a new observation, a galaxy brighter or more massive than theory predicted, the simulations must evolve too, growing ever more refined. Science, like the galaxies it studies, never stands still. Telescopes and simulations complement one another beautifully. One reveals what is, the other explores what might be. Together they turn the night sky into a readable history, allowing us to trace the universe's journey from its earliest whispers to the complexity we see today. Each photon we collect, each pixel we compute, adds to that grand narrative. If you could watch this story unfold, the real and the simulated side by side, you'd see the same themes repeat across time and scale. Clouds of gas collapsing into stars, galaxies merging and reforming, black holes igniting, quenching, and sleeping again. The universe builds itself with rhythm and grace, not unlike a musician repeating motifs in a vast cosmic symphony. Our instruments, humble as they are, allow us to hear just enough of that melody to recognize its beauty. There's also a quiet poetry in how the oldest light interacts with the newest technology. Photons that have travelled for over 13 billion years, older than the Earth, older than the Sun, are caught by mirrors polished by human hands. They fall onto detectors made of silicon and gold, are digitized into streams of data, and then turned into images that anyone on Earth can look at. It's as though the universe has been whispering for eons, and we've only recently learned how to listen. Every deep image is therefore both a scientific record and a work of art. The galaxies it contains are not frozen in time, they're caught mid-sentence in the long conversation of creation. Some are small and irregular, still assembling. Others already show spiral or elliptical shapes. Looking at them is like leafing through a cosmic photo album, each page taking us further back toward the beginning. And though we may never see the first stars directly, those brief brilliant pioneers that lit the universe's dawn, we can infer their presence through the faint glow they left behind and through the chemistry they seeded in later generations. Telescopes collect the light, simulations fill in the gaps, and together they tell the story of how darkness turned to radiance. When you gaze into a deep field image dotted with countless distant galaxies, you're not just looking at the universe as it is. You're seeing the memory of what it once was. Each speck of light is both ancient and immediate, the past made visible in the present. The sky, in this sense, is not a void, but a record, a living, luminous diary of cosmic time. And perhaps that's the most humbling truth of all, that even now, billions of years after the first galaxies began to glow, their light is still arriving, still unfolding across our skies. The universe has been writing its story since the beginning, and with our telescopes and our imagination, we have finally begun to read it. From the first faint ripples in a cooling cosmos to the grand architecture of the cosmic web, The universe has grown by listening to its own soft instructions. Gravity leaned into tiny imperfections and, with time as its patient partner, drew matter into filaments and nodes, leaving wide, quiet voids between them. In those intersections, dark matter halos formed like gentle valleys, invisible but sure, cradling the gas that would one day learn to shine. Cooling followed falling, heat became light, order rose from drifting fog. The long night began to open its eyes. Within those halos, gas remembered to turn. Angular momentum, the subtlest of nudges, gathered clouds into slow-spinning disks where stars could be born steadily rather than all at once. The first lights were giants, brief and brilliant, forging the universe's earliest metals and sending them outward in glorious endings that were really beginnings. Their explosions seeded space with carbon and oxygen and iron, the quiet pigments of future worlds. Dust formed, chemistry deepened, and light found curtains to filter through. With each generation, the cosmos became more adept at cooling and shaping itself, more capable of building stars and someday of building places to wonder about stars. As dawn spread, the fog lifted. Patches of ionized space grew, touched and merged until long sight lines opened across the deep. The cosmic morning settled into routine, and galaxies learned their crafts. Spirals refined the art of balance. Rotation holding the disk as gravity drew gas inward. Spiral waves tidally shepherding star birth into graceful arms. Bulges glowed like warm hearths. Bars ferried material to the center. Rings gathered where rhythms met. In this calm machinery, creation found a sustainable pace. Galaxies also learned to dance. Drawn together by the same gravity that built them, they met on long orbits, tidally stretching one another into streams and tails. Collisions unfolded as slow ballets, rearranging stars without striking them, compressing gas into starbursts, and, over ages, turning pairs of disks into rounded ellipticals with memories smoothed into amber. Even our own Milky Way carries the faint handwriting of such meetings. Tidal streams looping like ghostly ribbons across its halo, a bar glowing softly at its heart, a central black hole resting between quiet and flicker. At the centres of many systems, black holes tended subtle thermostats. Most days they were embers, hardly feeding, hardly heard. But in brief, loud seasons, accretion brightened them into beacons, their light and jet stirring, heating, sometimes sweeping gas out of the inner regions. Feedback could be a whisper or a gale, yet its long purpose was balance. Too much heat, and star formation paused. Too little, and it resumed. In this give and take, galaxies kept their poise, neither burning fuel in a reckless blaze nor falling forever into silence. Around the giants moved little lanterns, dwarf galaxies, abundant and sensitive, their lives written in flicker and rest. They were easily stirred by winds and tides, easily quenched near great neighbours, and yet they taught the clearest lessons. In their smallness, the rules of star formation and feedback and dark matter were drawn with clean lines. They fed larger systems through gentle accretion, became streams and halos, and kept the universe honest about its origins. Many small to fewer large, patient assembly over sudden invention. Environment shaped character. In crowded cluster cores, hot gas and relentless tides trimmed spirals toward maturity, building grand ellipticals that glowed in red serenity. On the outskirts, where the air was cooler and the space more forgiving, spirals kept their arms and their steady blue breath. Nature set the initial spin and mass. Nurture sanded and sculpted the rest. Across all of it, metallicity crept upward. Dust thickened the palette, and light learned new tones. Inevitably, many galaxies went quiet. Some exhausted their fuel, others kept it warm enough to be out of reach. Quenching worked from the centre outward in massive systems, and from the edges inward in those pressed by their neighbourhoods. The blue faded through the green valley to the soft golden red of age. Not an ending, but a long exhale, a dignified peace where old stars carried the memory of brighter days. Now and then, a surprise. A late infusion of gas, a small merger, a flicker of renewed birth. Even retirement in this universe allows for a gentle encore. How do we know this story? By catching ancient photons with mirrors of gold and glass, and by letting supercomputers grow miniature universes from simple beginnings. Telescopes read the sky's palimpsest, ultraviolet for hot youth, infrared for buried nurseries, radio for cold hydrogen and long magnetic threads. Simulations test the plot, asking whether gravity and time, with a few clear rules, can write what we observe. Together, observation and imagination braid evidence into narrative, and narrative into understanding. In that understanding, a mood emerges. Creation here is not a blaze, but a collaboration. Gravity proposes, time disposes, cooling and feedback edit the draft. The web is woven, halos are carved, gas gathers and rests. Stars flare and fade, and the result is not merely structure but temperament. Systems that breathe, pause and compose themselves over spans that dwarf the human scale. The universe is not hurried, it is devoted. So let the mind drift outward now to a vantage beyond the filaments, beyond clusters and their luminous cities. See the patterns settle into simplicity. Dark reaches, quiet voids, and across them countless galaxies like distant harbours. Islands of light in a calm, dark sea. Each island holds histories layered like sediment, ripples grown into webs, invisible valleys filled with morning mist, the first light scattering seeds, discs turned by rotation, dances concluded in amber, embers warming the core, lanterns circling the shores. All of it written by a few soft laws, repeated patiently until beauty emerges. If the night feels larger after this journey, let it also feel gentler. The same gravity that keeps feet to earth holds galaxies together. The same patience that cools a cloud kindles a star. Somewhere, bright rings are forming. Elsewhere, a bulge is settling. Far away, a dwarf is being drawn into a brighter future. And everywhere, the sea remains calm enough for islands to glow. Rest with that picture. The universe breathing slowly, the long collaboration continuing, and the sky above as a memory we can still read. The lights are steady, the water is dark and quiet. The distances are vast, but the story is simple. Gravity and time, weaving starlight into shorelines, one gentle wave at a time.